My latest project is a mind your head warning sign, triggered by an ultrasonic sensor, so it lights up when somebody gets too close. All powered by a Raspberry Pi Pico, and in this second video I'll be finishing it off, making the sign itself and a 3D printed case. I'll also be adding a buzzer as a final safety measure. But first let's remind ourselves where we got to in part 1, kicking off with the Raspberry Pi Pico and the ultrasonic sensor, wired up on a prototyping board, along with an LED, connected to one of the Pico's outputs. We got ChatGPT to write us some simple code to measure distances from the sensor, which we adapted to light our LED when something came too close. Finally upgrading that to a full flat panel backlight for our text display screen. And that's where we pick up the project for part 2, by making the screen itself. To make sure my dark areas are properly opaque, I'm going to be 3D printing it, but we start very much in 2 dimensions, with the type design, for which I'm using Adobe Illustrator, with my letters big and bold on a document the size I want the screen. There are of course other graphics programs you could use, but ultimately we want to end up with a standard vector graphic or SVG file, so just make sure whatever you use is compatible with that. Illustrator is also good because we've got quite a lot of control over the type, enabling us to space it as we want, with quite large gaps between each letter, so each one stands out individually when backlit. We also want the bit in the middle where the 2 screens meet to be covered rather than falling in the middle of a letter. When we're happy, we need to export it as the SVG, selecting that from the drop-down. Obviously other software may well do this very differently, but the options are likely to be similar, and we can probably just use the defaults. But there is one setting which may be unique to Illustrator, which I'll come along to in a moment. For our 3D design, I'm going to be using Tinkercad, entering the measurements for a block the size of our sign. It's a really great bit of software, especially as it's free, but for type it's a bit basic, which is why I've gone for importing my text as an object, dragging my SVG to the panel, and hitting the import button should bring it in as a new shape. I say should because actually we hit a problem, getting an error message about unsupported elements. So it's back to Illustrator to give exporting another go, as Tinkercad obviously didn't like one or other of the settings I used, and we're going to have to methodically work out which one, renaming our export so it doesn't get mixed up with the previous one. Fortunately there are not too many things it could be, and perhaps the easiest is to try out converting the text to outlines, which feels like a good place to start, as that will turn each letter into a vector object of its own, rather than relying on embedded fonts. And sure enough, hitting the import button this time successfully brings in our type, extruded into a 3D object. Now one thing I don't understand is the scale it's come in at, as both my Illustrator file and the Tinkercad are set to the same size, but easy to remedy by dragging one of the handles whilst holding down the Shift key to constrain the proportions, until we're happy with the size and position. The scaling has also affected the height, leaving us with a rather random fraction, so I just want to round that up to a whole number. At the moment our type is a solid, so our letters would print raised above the block, which is obviously no good to us. We want them to be cut out, but not through the entire thickness, so I'm raising them up off the work plane by 0.6 mm, which will leave 3 layers of print below the cutout type. This is achieved by turning the text into a negative whole, and with the blocks selected as well, grouping into a single object. But why the solid base layers? Surely they'll stop the light getting through as well, but we need something to hold the middle bits of some of the letters in place. So my cunning plan is to print those in transparent filament, then switch to black to print the stencil part, making a screen. And suitably named, we can now export as an STL file, ready for slicing. For this I'm using Ultimaker Cura, another bit of free software, dragging my STL onto the build plate. Then before slicing I want to rotate it 45 degrees, not in this case because it doesn't fit, but because I want some nice straight lines rather than diagonals, particularly on the transparent layers, giving me a weave rather than a crisscross effect from any of the print lines that are bound to be visible. It's here, after layer 3, that I want to change my filament, the rest printing in black. And although I'm sure that there must be some way of programming this into the G-code, I'll be adopting a more basic approach, estimating the elapsed time before doing the switch over on the fly. And now, with the sliced file loaded up onto my Ender 3 Neo, let's get printing and find out how well I get on. This is the first time I've used a clear filament, and I've actually been pleasantly surprised by how well it's worked. Here you can see how by putting my design at a diagonal, the print head lays down nice long straight filament lines, gradually filling the width, to form a pretty smooth first layer. Better, I think, than a zigzag of the diagonal lines from the usual orientation. Then, with the first layer done, it's back round the skirt for layer 2. This time the print head moving backwards and forwards parallel with the short sides, filling the layer along the length. It might appear to be doing this more quickly, but of course it's got more lines to do, so actually takes about the same time. And the length of time is important to us, because with that we can calculate when we need to switch the filament, bearing in mind the entire length of the Bowden tube is still full of clear. And by my calculation, that's about the next layer's worth. So as the printer finishes this one, we need to brace for action. We've actually got quite a reasonable leeway, as it doesn't matter that much if layer 4 starts printing in clear. So we've got time to calmly snip through that, about an inch away from the extruder, and carefully remove the filament reel, making sure we don't jog the printer. An added complication in my setup is that my homemade bearing doesn't fit all types of spool, but it's easy to turn round for those that it does. And with my black filament loaded up and the end snipped off at an angle, we're ready for it to follow the clear down through the hole in the extruder, which in the time it's taken us to switch the reels is even now only just about to disappear. When the new filament's inserted, we need to continue guiding it in until the gears on the extruder have got a grip on it, also watching out for any retraction when the extruder pushes the filament back on itself. But when we see the reel turning, no matter how slowly, we know the changeover is complete and the black is following the clear down the tube, heading for the print head, which is still currently printing clear. And we can see it has started layer 4, the outlines of some of the letters taking shape, with a little bit more to go, judging by what's left in the tube. This method is undeniably a bit basic, but actually works pretty well, but only if you've got quite a lot of tolerance for the colour changeover, like we have here, where by the start of layer 5 the black is now printing, only one letter behind the rest, and will carry on to the top of the print, with what's now 6 layers to go, by which time that tiny difference will be buried at the bottom of the stencil. And drama over, we can let the printer get on with the rest, until we get to the top layer at 2mm thick, finishing up with 4 layers of clear and 6 layers of black. Slightly more of the clear than I'd estimated, but still plenty of the stenciled layer to block out any light. Then, having waited for everything to cool, we can release our sign from the print bed, and after cleaning off any loose strands of filament, put it to the test on the circuitry we finished in part 1. My hand's close enough to trigger the LEDs. With our screen complete, we've now got a working model, and the next stage is to package it up with a nice case to hold everything together. So it's back to Tinkercad, where I've designed the top part of this with a kind of tray for the LEDs, and circular cutouts for the ultrasonic sensor. You can also see I've found a way of getting the radiused edges only on the top part of the blocks, the bottoms being buried under the work plane, disappearing when the whole thing's grouped. I've also found a way of excluding parts from any grouping, which is to lock them first, so it doesn't matter if they're buried under other stuff and you can't get to them to deselect. But this isn't really intended to be a Tinkercad tutorial, and all my finished files are available to download from my website, so you can print your own if you want, and if you do, please give me a shout out on social media, and of course, don't forget to subscribe. Then with slicing done, it's onto the printer, where I've switched to bog standard grey filament, just while I get my prototyping done. I'll have to have a think about what colour I want the finished thing to be. Eventually, that's also going to be a bit longer, to make space for my buzzer. So like my screen, I'll be printing on the diagonal, but at the moment it fits fine width on. I'll also be waiting for the final design before doing the bottom half, although you can already see that I've got some screw holes in anticipation of how they're going to fit together. But before all of that, let's do a first assembly, uniting our new 3D printed bits with the Pico and the other circuitry, where we'll be gradually migrating the parts from the breadboard. The first of these are my LED panels, which are going to fit into the tray on the top of my case, the sides of which are shaped so the leggy ends will tuck under the frame, the legs themselves folding underneath, where for now they'll plug into the same cables. As you can see, they butt up nicely in the centre of the screen, with any visible join there is hidden by the stencil of my letters, and with a little flex of the legs they will lie flat, ready for the screen to go on top, which neatly clips into place, sandwiching the LED panels in between. Then flipping the whole thing over, we can very carefully fold round the legs, using a spare scalpel handle to ensure a gentle curve, reducing the risk of any breakages. First at one end and then the other, before plugging in our cables again, making sure we get the pale one on the anode and the dark one on the cathode. You'll notice the orientation appears to be different at either end, but is in fact the same, with the folded under anode of each on the left, meaning we've got both screens the right way up, with the reflector on the back. Then it's onto the sensor, unplugging it from the breadboard and inserting into the 2 holes on the case. At the moment they stick out quite a bit, but we can adjust that later when I come on to do the back. We'll also be completely redoing the wiring, with everything including the Pico inside the case. But for now I've got a ribbon cable to connect it up to exactly where it was on the breadboard, making sure the pins are in the right order. Checking the labels on the front of the sensor if necessary, particularly important if, like mine, the colours are different to those on the breadboard. Then, with both LED panels and my ultrasonic sensor fitted and wired to the front of the case, time to plug in and make sure everything works. The USB power supply automatically running the main program on the Pico, triggering the lights when something comes within a foot. But to make absolutely sure nobody bumps their head, I want to add an audio warning, triggered when somebody gets really close. And for this I've got a buzzer, which even though it's rated at 5 volts, should be good for our 3 volt system. Eventually, like everything else, that will end up inside the case. But for now it's going in the breadboard. As well as having a slightly longer leg, the positive is well marked, and I've got a green wire for that, black for the negative. The other end of the green wire connecting to a spare GPIO pin on the Pico. I'm using the one next door to the output pin for the LEDs, and likewise the same ground, plugging in the black wire next door. Then, even though my wiring appears messy, I've got neat consecutive pin numbers, so at least my program will be a bit tidier. And that's what we come to now, connecting up to the host computer and launching Thonny so we can see the files on the Pico. Here's main.py, the one that runs automatically, an exact copy of Echo 1. And it's that I want to save as another duplicate, also on the Pico, so I can edit in the changes I need for the buzzer, without losing the original, just in case I want to go back to that for any reason. My first change is a general one, which is to slow down the sampling rate, so it pauses between readings for a bit longer. It'll still be pretty responsive, just not quite as twitchy as before. Then we want to set up the pin for our buzzer, using the same format as for our LED, but with 17 instead of 16. And again, that's a pin out. Now to get it to do something. And first of all, I want to tell it to buzz when the light lights up. And for that, I can simply copy the LED code, replacing warning with buzzer, which as it's passive, is just either on or off, just like the LED. So can be given a value of 1 or 0 for each state. And now when we run the code, the measuring bit calculates the distance, and if that's less than 30 centimeters, the lights light and the buzzer sounds. So far, so good, but we don't really want the buzzer going off all the time, only as a last resort if someone gets very close, and for that we can set up a check within a check. In this part of the code we've already established that something's within 30 centimeters and lit the LED, and now we want to see if something's within 10 centimeters, so we can buzz the buzzer. And if it isn't, stay quiet and just have the visual warning with a buzzer value of 0. And if our first check comes back with nothing closer than a foot, the second check would just get skipped, so we don't need this line. So now, when anything gets closer than 30 centimeters, lighting the light, our program will also check if anything's closer than 10 centimeters, and buzz the buzzer, providing us with 2 levels of warning of increasing urgency. Now all that remains is to make this version the one that runs automatically. We've already got a copy of the old one as Echo 1, so it's safe to delete that. And once again, doing a save as, create a new copy of Echo 2, also called main.py, just like the old one, so the Pico knows that that's the one to run when we power up our sign away from the host computer. And with all our coding and prototyping done, that's what we want to finish off in the final assembly. To accommodate my buzzer, I've made the front case a little longer, cutting out a cylinder the size of its body, with a smaller hole right through the case for the sound to get out. And as it is longer, I'm printing it this time on the diagonal, having finally plumbed for a milky white filament, which will contrast nicely with the black of the screen. I've also now got a design for the other half of the case. At the moment that still requires a little tweaking. You'll see where I've got to in a moment. But when that is finished, it'll also be available to download from the link in the description. But before I put everything in the case, I've got one final adjustment to make, and that's to optimize the brightness of the screen. And after a bit of testing, I've decided on a lower value resistor of just under 60 ohms, quite a bit less than before, but still enough to give my LED screens some protection, whilst making them quite a bit brighter. Then, with all my case parts printed and final adjustments to the hardware made, it's time to get on with the final push and get everything off of the breadboard and into the case, unplugging the jumper cables from my LEDs and the ribbon cable from the ultrasonic sensor, which can be put to one side for now. And with its job done in the development of the design, I can disassemble the previous grey version of the front case, carefully bending back the legs of the LEDs and unclipping the screen, prising up the edge with the tip of a scalpel and popping it out, giving us access once more to the LED backlights, which can be lifted out, legs still bent backwards so we'll know which way to put them back in again, with the reflective surface at the back. Other than the extra length and the accommodation for the buzzer, my new case front is the same as the old one, so I'm expecting all my parts to slot in exactly as before. With the legs already folded back, my LED panels slot in easily, butting up end to end. Then it's in with the screen, which fits a little looser than before, so rather than clipping in place will require a bit of glue, but I'm going to wait and see that everything works properly first, before finally sticking it in place. Then it's back round with the legs of the LEDs, which have mercifully survived the bending and unbending without snapping. As expected, my ultrasonic sensor also fits the same as before. But now I've got a design for the case back, I can start thinking about how much I want sticking out the front, and how deep the back needs to be for that to fit. Hopefully the only adjustment necessary. But as well as the sensor, we need room for our Raspberry Pi Pico. And here I'm making the biggest change to our prototype, switching out the one with the soldered headers for a bog standard Pico, which I've already set up with MicroPython and started loading up with the software that we had on the other one, temporarily downloading to my host computer before copying over to the new one, finishing up with the all-important main.py, itself a copy of Echo 2, and we've still got the other programs just in case we need them. Then, securing the screen to the case front with a couple of blobs of white tack, just so it doesn't fall out, we can flip the front on its face, ready for the Pico. In my design, everything fits to the inside of this half of the case, with a USB cable already attached to the Pico, trailing out of a slot in the side of the back, long enough to reach my power source. Ideally, it would be nice to plug that into a socket, but the fixed wire will do for now, and we'll attach that right at the end when all the wiring's done, just before closing the case. My Pico's held in with a double-sided sticky pad, simply stuck to the back. I've trimmed this slightly narrower than the board, so it doesn't melt when I solder the terminals. And just lining up to make sure I get it straight. That'll stick down inside the case front, just off to one side, with plenty of room all round for the wiring. My sensor will also need a permanent fixing, but not just yet, so in the meantime a couple of blobs of white tack can hold it in place. And with nearly all my components assembled, I can get on with soldering the wires. This is really a case of replicating what I had on my breadboard, and I'm going to start with the LED panels, trimming the legs so there's less to get in the way, but leaving the anodes a little longer so I don't forget which is which. The wire I'll be using is a 32 gauge decoder wire from DCC Concepts, which I use in all my model railway conversions, the fine gauge making it easy to manipulate, although stripping the ends requires some care, and preferably some precision wire strippers, to get a good length to solder onto the legs of our LED, red on the anode, black on the cathode. Then I want to slide on some heat shrink insulation to cover the soldered join. This will not only prevent any shorts should the legs touch each other, but will also help support the fine wire, which is particularly vulnerable at the join. I'll be waiting until I've tested everything before shrinking it down. Then with one end done, onto the other, spreading the solder the entire length of the stripped end, so we get a really good electrical connection on all 4 of the terminals. And soldering done, we can trim the wires and slide on our heat shrink before going on to the other end, where we're going to attach to the Pico. And to remind myself where everything goes, I'm pulling up the breadboard. So all we have to do is copy that, starting with the resistor, which I'm just straightening out, trimming off one end to about 1 centimeter and bending round the end. This is the positive for our LEDs, and just like on the breadboard, we're going to connect it to pin 16, the one in the corner of the Pico. And just to keep everything neat and tidy, I'm going to solder it at right angles so it lies across the end of the board. To the other end I need to attach my 2 red cables, again exactly like it was on the breadboard, only this time I don't have the luxury of multiple connectors, so I'm going to need to join them together. And not forgetting my heat shrink insulation, line them up carefully where they can be soldered to the other end of the resistor, again making sure we've got a really solid join for both of our wires, finishing up by sliding over the insulation, which will also help support the wires. For the cathodes of the LEDs, we've got a slightly simpler job, as our black wires can be connected directly to any of the ground pins on the Pico, indicated by the square ends. And as this is a common negative all around the board, they don't even need to go to the same one. So it's just a case of trimming to length and stripping the ends before soldering to a convenient location. And that's our LED panels done. Now to wire up our sensor. And to make this easier, I'm removing it from the case for the time being and sticking it onto my soldering mat, using those blobs of white tack, just to hold it nice and still while I solder wires to each of the terminals. This not only makes everything easier to get at, it also means we can see the labels on the sensor, so we can solder an appropriately coloured wire to each one. And I'll be following the same colour scheme as I did for the breadboard version. Red for the VCC, yellow for the trigger, blue for the echo, and obviously black for the negative. Then there'll be no confusion when we come to solder the other ends to the Pico. As with the LED connectors, I'm also slipping on some heat shrink, not really for insulation, but mostly to support the fine wire at the join with the leg, preventing it from bending and breaking during installation and afterwards. And confident with my connections, I'm shrinking it now, using the slightly cooler barrel of the soldering iron. Then with the sensor reinstalled, we can solder the other ends of each wire to the Pico, starting with the black, which, like the ones on the LEDs, can go to any one of the ground pins. Then it's a case of working back through the other wires, and having used the same colours as my prototype, I can refer back to the breadboard as a guide, as it still has the jumper cables in it. And reminded that the blue wire for echo goes to pin 18, we can stick the end into the hole and solder in place, followed by the yellow trigger wire, which connects to pin 19 just next door, giving us a soldered facsimile of what we had on the breadboard. Finally, the red wire, which not having far to go, we can trim and strip, soldering to the 3.3 volt output, the fifth pin in from the right hand end of the board, getting us to where we were at the end of part 1, which before going on to fit the buzzer is probably a good time to test what we've got and make sure everything works. Then we can do the finishing touches of this stage, tidying up the wires and shrinking the insulation. That just leaves the buzzer, the last component to migrate from the breadboard, leaving only the prototyping Pico behind. This fits pretty snugly into my case, pushing into the cylindrical hole I've left in my 3D print, with room enough in the back case to accommodate the bit sticking out, although I'll need to bend round the legs as soon as they're soldered. And the procedure here is exactly the same as for the other bits. Red wire on the longer positive leg, black on the other. Then the other end of the red one can be guided to pin 17 on the Pico and soldered in place, followed by the black wire trimmed to a convenient length so it reaches the nearest ground pin, which just happens to be the one it used on the prototype. And as my buzzer wiring is all pretty short, I'm not going to bother with the heat shrink. So that's all the wiring done, and all that remains before assembling the case is make sure everything works. So it's back in with the USB power supply, which will automatically run the main.py program, lighting the light and buzzing the buzzer if anything gets too close. So with everything fully operational and all of our hardware checked, we can close up the two halves of the case, threading the power cable through the indent that I've left for it. I've also got some hexagonal holes in the bottom, into which I can push some M2.5 nuts, which need to go right to the bottom, and I found the easiest way of doing this is to push them in with the head of the corresponding bolt. And when the nuts are deep enough, the bolt should engage with them when inserted from the front of the case. Then, tightening with the hex key, they'll be pulled up the rest of the way for a nice tight fit. And once all four corners are done, the two halves of the case are secure with all the gubbins inside. I've also glued the front screen, so that's not going to fall out either. And that's my sign pretty much complete. I'll almost certainly need to make some tweaks to the software to get my trigger distances right, and of course mount it where it matters, preventing any avoidable headaches.